Lava flows from the world's largest volcano is raising fears it could reach a main highway within a week. The active Mauna Loa volcano in Hawaii erupted for the first time in nearly 40 years.
How do you think the world's going to end? Maybe a meteor crash or a massive flood? Well, the real threat may be lying under our feet. This is a map of the Pacific Ring of Fire, a volatile belt of seismic activity encircling the Pacific Ocean. Here lies Mauna Loa, the world's largest supervolcano, whose awakening could spell catastrophe on a global scale. Imagine a scenario where an eruption triggers massive tsunamis, blanketing continents in ash, and leading to an unparalleled global crisis. Supervolcanoes have actually claimed more lives than asteroids, and recent studies have revealed that they're far more dangerous than we ever imagined. With Mauna Loa stirring from its slumber, the question arises, are we on the brink of witnessing a supervolcanic eruption that could rewrite the very story of life on Earth? Let's find out. In the vast annals of Earth's history, few natural phenomena have been as awe-inspiring and terrifying as volcanic eruptions. Their power, capable of altering landscapes and climates, has long been a source of myth and legend. But beyond these tales lies a chilling reality. Volcanoes possess the real and potent ability to unleash catastrophic scenarios, potentially even leading to the eradication of humanity. What if the next volcanic eruption were not just a localized disaster, but a cataclysmic event with the power to plunge our world into chaos? Recent reports have now surfaced, revealing that Mauna Loa, a volcano known for its colossal size and power, has begun to stir, a possible prelude to an eruption of unprecedented scale. But it's important to establish some context behind volcanic eruptions before we dive into the details. Imagine a world plunged into darkness, not for days, but for years. Volcanic eruptions have the capacity to spew massive quantities of ash and gases into the atmosphere, creating a veil that obscures the sun. This isn't mere speculation. It's a scenario backed by geological evidence. Historical records and geological studies have shown that super eruptions have led to volcanic winters, where the sun's rays are dimmed, leading to catastrophic drops in temperature. The impact of such an event is not just discomforting cold, but a chain reaction that could spell disaster for life on Earth. Agriculture would collapse, food chains would be disrupted, and a struggle for survival would ensue. Is humanity ready to face such a challenge? Or are we woefully unprepared for the fury that lies beneath the Earth's crust? What makes this scenario even more alarming is the unpredictability of such eruptions. Despite advances in technology and monitoring techniques, predicting the exact timing and magnitude of supervolcanic eruptions remains a significant challenge. The signs, seismic activity, ground deformation, gas emissions can be difficult to interpret, and the window for taking action might be frighteningly small. The potential for widespread chaos and destruction from a supervolcanic eruption begs the question, could such an event lead to the extinction of human life on Earth? The answer lies in history. Approximately 74,000 years ago, the eruption of the Toba supervolcano in present-day Indonesia is believed to have caused a volcanic winter lasting several years, leading to a dramatic reduction in the global human population. While humanity survived, the event serves as a stark reminder of the fragility of our existence in the face of Earth's powerful natural forces. Moreover, supervolcanoes are not the only volcanic threat. Even regular volcanic eruptions have the potential to cause widespread disruption. The eruption of Mount Tambora in 1815 led to the year without a summer, with global temperatures dropping and resulting in food shortages across the northern hemisphere. The effects of such eruptions on today's densely populated and interconnected world could be far more catastrophic. The seismic activity that often precedes massive eruptions also poses a significant threat. Earthquakes, tsunamis, and landslides can all result from volcanic activity, each with the potential to cause widespread destruction. The 2004 Indian Ocean tsunami, triggered by an undersea megathrust earthquake, is a stark reminder of the destructive power of these seismic events. Can our modern infrastructure withstand such forces, Or are we living on borrowed time, hoping to evade the inevitable? The chilling truth is that despite advances in technology and monitoring, predicting the exact timing and scale of a volcanic eruption remains a challenge shrouded in uncertainty. Volcanic activity is complex and multifaceted, often giving little warning before an eruption. The monitoring systems in place, while advanced, are not foolproof. They provide valuable data, but can they give us enough time to react and mitigate the consequences of a catastrophic eruption? The question then arises, are we prepared for what lies ahead? Scientists have just made a groundbreaking revelation. As if roused from a deep slumber, Mauna Loa, the behemoth of volcanoes, is stirring. This colossal force of nature, nestled on Hawaii's Big Island, isn't just another volcano, it's the largest active volcano on Earth. Its awakening raises alarms and poses pressing questions about our preparedness for a potential eruption that could rewrite history. Mauna Loa's history is as expansive as its massive footprint. Spanning approximately half of the Big Island, its name, translating to Long Mountain in Hawaiian, is a fitting description for this mammoth shield volcano. Mauna Loa's significance stretches far beyond its geographical size. It's an integral part of the Hawaiian Islands' formation story, having risen from the ocean floor over thousands of years due to the Pacific Plate moving over a hot spot in the Earth's mantle. This process has been ongoing for at least 700,000 years, with Mauna Loa being one of the youngest volcanoes in this island chain. But what lies beneath this seemingly tranquil mountain? Mauna Loa's geological structure is a marvel in itself. The volcano is characterized by long, gentle slopes formed by low-viscosity lava flows. These flows have created a shield-like shape, which is typical of the Hawaiian volcanoes. At its summit, Mauna Loa hosts the Mokuaweo caldera, a large depression formed by past eruptions. The volcano also features two rift zones extending northeast and southwest, where the majority of its eruptions originate. These rift zones are areas where the volcano's flank is rifting or splitting apart, providing pathways for magma to reach the surface. Throughout history, Mauna Loa's eruptions have been a spectacle of nature's might. The volcano has erupted 33 times since its first well-documented eruption in 1843. Each of these eruptions has contributed to the understanding of volcanic behavior. Perhaps the most significant of these was the eruption in 1950, known for producing one of the fastest lava flows recorded. The flow reached the ocean within less than 3 hours after the start of the eruption, a vivid reminder of the speed and destructive potential of volcanic activity. This brings us to a crucial point. Are we truly prepared for the next eruption? As Mauna Loa awakens, scientists and authorities are on high alert. The United States Geological Survey closely monitors the volcano for signs of activity. Changes in seismic activity, ground deformation, gas emissions, and temperature changes are all carefully analyzed. These monitoring efforts are not just for academic interest, but are critical in providing early warnings to residents and authorities for evacuation and emergency response planning. Yet, despite the advancements in technology and monitoring techniques, predicting the exact timing and impact of an eruption remains a challenge. Mauna Loa's history is a testament to the fact that eruptions can occur with little warning, and their impacts can be far-reaching. In this context, understanding the Pacific Ring of Fire becomes crucial. This horseshoe-shaped area in the Pacific Ocean is a hotbed of seismic activity, including earthquakes, volcanic eruptions, and tectonic plate movements. Stretching from New Zealand along the eastern edge of Asia, across the Aleutian Islands of Alaska, and down the coasts of North and South America, the Ring of Fire is home to over 75% of the world's active and dormant volcanoes. This region, where tectonic plates collide and dive beneath one another, is a constant reminder of the Earth's dynamic nature. But what makes the Pacific Ring of Fire particularly noteworthy? It's not just the number of volcanoes, but also the variety and intensity of volcanic activity. This region includes some of the world's most notorious volcanoes, such as Mount St. Helens in the United States, Mount Fuji in Japan, and Mount Ruapehu in New Zealand. Each of these volcanoes has its unique characteristics and history of eruptions, contributing to our understanding of volcanic behavior. The recent volcanic activities in the Ring of Fire have had global impacts. The 2011 eruption of Mount Merapi in Indonesia, one of the most active volcanoes in the Ring of Fire, led to the evacuation of hundreds of thousands of people and affected air travel across Southeast Asia. In 2020, the eruption of Taal Volcano in the Philippines spewed ash up to 14 kilometers into the air, disrupting flights and causing thousands to flee their homes. But what does the future hold for the Pacific Ring of Fire? As tectonic plates continue to shift and collide, the potential for more eruptions remains. The communities living along the Ring of Fire have adapted to this constant threat, developing early warning systems, evacuation plans, and building structures designed to withstand seismic activity. Within this volatile Ring of Fire lies Mauna Loa, a quintessential example of the immense power and unpredictability of Earth's volcanic activity. If Mauna Loa were to erupt, the potential risks and impacts would be immense. Given the volcano's history of producing large, fast-moving lava flows, an eruption would pose significant threats to nearby communities. In the past, its lava flows have reached the ocean in just a few hours, destroying everything in their path. A major concern is the lava flow's direction and speed, which could cut off critical infrastructure, including roads and power lines, and potentially engulf residential areas. But it's not just the lava flows that are a cause for concern. The release of volcanic gases, particularly sulfur dioxide, can lead to air quality issues, affecting not only the immediate area around the volcano, but also downwind communities. In large enough quantities, these gases can create volcanic smog, or VOG, which can have serious health implications, especially for individuals with respiratory issues. Furthermore, an eruption of Mauna Loa could have far-reaching economic impacts. The Big Island of Hawaii is a popular tourist destination, and an eruption could disrupt air travel and tourism, a vital part of the island's economy. The ash and volcanic gases emitted during an eruption could also have implications for agriculture, another key sector of the island's economy. Recognizing these potential risks, the Hawaii County Civil Defense Agency has developed comprehensive emergency response plans. The plans outline how to evacuate large numbers of people quickly and safely, taking into account the possible directions of lava flows and the roads that could be affected. Emergency shelters and supply depots are strategically located to support displaced populations. But as crucial as these preparedness plans are for mitigating the impact of Mauna Loa's eruptions, it's essential to understand the distinct nature of supervolcanoes like Mauna Loa. The term supervolcano might sound like something out of a science fiction novel, but it is a very real and sobering geological concept. The power and intensity of a supervolcano far exceed those of typical volcanic eruptions. While regular volcanoes can certainly cause significant damage, supervolcanoes have the potential to produce eruptions that are thousands of times more powerful. The key factor that classifies a volcano as a supervolcano is its capacity to eject more than 240 cubic miles of material in a single eruption. To put this into perspective, this is enough volume to fill over 400,000 Olympic-sized swimming pools. But where are these sleeping giants located? And what do we know about them? There are several supervolcanoes around the world, each harboring the potential for enormous eruptions. The Yellowstone caldera in the United States, the Toba caldera in Indonesia, and the Taupo volcano in New Zealand are among the most well-known. Each of these supervolcanoes has a history of colossal eruptions that have left indelible marks on the Earth's surface and atmosphere. For example, when the Taupo volcano last erupted over 26,000 years ago, it ejected an estimated 1,170 cubic kilometers of material, a volume so vast that it could fill the Grand Canyon in the United States. This eruption drastically transformed the landscape and had significant climatic impacts, demonstrating the immense power of supervolcanoes. And what drives these gargantuan eruptions? The science behind supervolcanic eruptions is a blend of factors that come together in a dangerous and volatile mix. A supervolcano's magma chamber, the underground pool of molten rock, is key to its explosive potential. These chambers are much larger and contain significantly more magma than those of regular volcanoes. For example, the Yellowstone caldera has an enormous magma chamber that extends for dozens of miles. This vast reservoir of molten rock is under immense pressure, and when this pressure builds up enough to break through the Earth's crust, the result is a supervolcanic eruption. The mechanics of these eruptions involve not just the ejection of lava, but also colossal amounts of ash, gas, and rock. When a supervolcano erupts, it can eject so much material that it leaves a massive depression or caldera in its wake. This is not just a hole in the ground, it's a vast, gaping wound on the Earth's surface, evidence of the volcano's explosive power. The eruption of a supervolcano is not a local or regional event. It's a global disaster. The ash and gases released can spread around the globe, affecting climate, agriculture, and health on a scale that is hard to comprehend. At the heart of every volcanic eruption is a process that begins deep within the Earth. It's a journey that starts with magma, the molten rock beneath the Earth's surface. Magma is formed when the Earth's mantle melts, a process influenced by factors like temperature, pressure, and the presence of water. As this magma becomes less dense than the surrounding rock, it begins to rise. The path it takes to the surface and what it encounters along the way plays a significant role in the type of eruption that will occur. But how does this magma actually break through the Earth's crust? This is where the role of gases within the magma, such as water vapor, carbon dioxide, and sulfur dioxide, becomes crucial. These gases are dissolved in the magma when it's under high pressure deep within the Earth. As the magma rises, the pressure decreases, and these gases start to come out of solution, forming bubbles. The expansion of these bubbles increases the pressure within the magma, eventually leading to an eruption. Now, let's delve into the different types of volcanic eruptions: explosive and effusive. These two broad categories describe the way a volcano erupts, and they are largely determined by the viscosity of the magma and the amount of gases it contains. Explosive eruptions occur when the magma is high in viscosity and rich in gases. The high viscosity, often due to a high silica content, makes it difficult for the gas bubbles to escape, leading to a buildup of pressure. When this pressure is released, it results in a violent explosion, ejecting ash, lava, and volcanic gases high into the atmosphere. These eruptions can be incredibly destructive, as seen in the 1980 eruption of Mount St. Helens. On the other hand, effusive eruptions occur when the magma is low in viscosity, allowing gases to escape more easily. This type of magma flows smoothly out of the volcano, forming lava flows that can cover large areas but are generally less explosive. A classic example of effusive eruption is the Hawaiian volcanoes, where lava flows gently down the slopes, creating spectacular fire rivers. But what determines whether a volcano will erupt explosively or effusively? It largely comes down to the magma's composition. Magma can be broadly categorized based on its silica content: basaltic, andesitic, dacitic, and rhyolitic. Basaltic magma, which has the lowest silica content, typically leads to effusive eruptions. As the silica content increases, the magma becomes more viscous, leading to more explosive eruptions. The rhyolitic magma, with the highest silica content, is associated with the most explosive volcanic eruptions. Now, let's consider some real-world examples that illustrate the profound consequences of volcanic eruptions. Krakatoa, Mount St. Helens, and Vesuvius serve as powerful case studies, showcasing the immense power and far-reaching effects of volcanic events. The eruption of Krakatoa in 1883 is etched in history as one of the most catastrophic volcanic events ever recorded. Located in the Sunda Strait between the islands of Java and Sumatra in Indonesia, Krakatoa's eruption was heard as far away as Australia and the island of Rodriguez near Mauritius, over 3,000 miles away. The eruption ejected more than 25 cubic kilometers of rock, ash, and pumice, and generated massive tsunamis that devastated numerous towns and villages along the coasts of Java and Sumatra, killing over 36,000 people. The global climate was significantly affected as well, with temperatures dropping by an average of 1.2 degrees Celsius in the year that followed. The eruption of Krakatoa served as a wake-up call to the global community about the potential global impact of volcanic eruptions. Mount St. Helens, located in the state of Washington, U.S., erupted on May 18, 1980. This eruption, the most significant in U.S. history, blasted away a large part of the mountain, reducing its height by about 1,300 feet and forming a huge crater. The eruption killed 57 people and caused immense property damage, including the destruction of 250 homes, 47 bridges, 15 miles of railways, and 185 miles of highway. Beyond the immediate destruction, the eruption had significant environmental impacts, including the devastation of 230 square miles of forest. The Mount St. Helens eruption fundamentally changed the landscape and ecology of the surrounding area, but also marked a significant advancement in volcanic research. It led to the establishment of the Volcano Disaster Assistance Program and improved volcanic monitoring and prediction capabilities. Another historically significant eruption is that of Mount Vesuvius in 79 AD, which buried the Roman cities of Pompeii and Herculaneum. This eruption is notable for its preservation of the artifacts and bodies of those who perished, providing a snapshot in time of Roman life. The tragedy of Vesuvius serves as a stark reminder of the potential loss of life and cultural heritage that can result from volcanic eruptions. The study of Vesuvius and its eruptions has contributed greatly to our understanding of pyroclastic flows and volcanic archaeology. Just as Vesuvius is etched in history, another formidable giant quietly looms over the United States, the Yellowstone supervolcano. Nestled atop one of the most geologically active areas on Earth, the Yellowstone caldera is a dormant giant with the power to alter life as we know it. Often referred to as a supervolcano due to its capacity to produce an eruption of immense scale, Yellowstone's volcanic system is a complex and mystifying geological feature that has intrigued scientists and the public alike. The caldera itself, measuring about 55 by 72 kilometers, is a colossal volcanic depression formed during the last three super eruptions, occurring 2.1 million, 1.3 million, and approximately 640,000 years ago. The geological features of Yellowstone are as fascinating as they are terrifying. Beneath the scenic landscapes of geysers and hot springs lies a vast magma chamber, estimated to be approximately 60 kilometers long, 29 kilometers wide, and up to 15 kilometers deep. This immense reservoir of molten rock is the fuel for the supervolcano's potential eruptions. The most recent significant eruption formed the Lava Creek Tuff and drastically altered the topography of the region. Despite its current dormant state, the caldera is anything but inactive. The frequent geothermal activities, like the erupting geysers and hot springs, are surface manifestations of the intense heat and dynamic processes occurring deep underground. The Yellowstone supervolcano's eruption history is a subject of intense study and fascination. The three catastrophic eruptions that occurred millions of years ago were so massive that they ejected vast amounts of ash and lava over large portions of North America. These events dramatically impacted the climate and ecosystems, with the effects felt globally. The ash from these eruptions can still be found across the United States, serving as a stark reminder of the volcano's immense power. Yellowstone is one of the most closely monitored volcanic regions in the world, with a network of seismometers, GPS stations, and other geological sensors continuously tracking its every move. The Yellowstone Volcano Observatory, a collaborative effort between the U.S. Geological Survey, the University of Utah, and Yellowstone National Park, is at the forefront of these efforts. But even then, predicting an eruption at Yellowstone remains a formidable challenge due to the sheer size and complexity of Yellowstone's volcanic system. For instance, increased seismic activity, a common precursor to volcanic eruptions, is a regular occurrence at Yellowstone, making it challenging to discern whether such activity is routine or a sign of something more ominous. But this challenge pales in comparison to the enigmatic world of underwater volcanoes, a realm largely unexplored and full of mysteries waiting to be unraveled. Underwater volcanoes, also known as submarine volcanoes, are hidden giants beneath the ocean's surface. These submerged behemoths are as fascinating as they are elusive. They form a significant part of Earth's volcanic activity, yet their remote location makes them incredibly challenging to study. The exploration of these underwater volcanoes has largely been a 20th and 21st century endeavor, involving advanced technology like remotely operated vehicles, sonar mapping, and satellite imagery. These tools have allowed scientists to peer into the depths of the oceans, uncovering a world of fiery mountains, some even larger than their terrestrial counterparts. The unique characteristics of underwater volcanoes present both wondrous and daunting aspects. Unlike volcanoes on land, the immense pressure of the ocean depths dramatically alters how these volcanoes erupt and how their lava cools and solidifies. The intense pressure prevents the formation of large gas bubbles, which in turn typically leads to less explosive eruptions compared to those on land. However, when these volcanoes do erupt explosively, they can form new islands overnight or send massive tsunamis racing towards distant shores. The discovery of hydrothermal vents and black smokers on these underwater mountains has also opened up new avenues of research into the origins of life, offering insights into a world where life thrives in extreme conditions, far from sunlight. Notable underwater eruptions and discoveries have reshaped our understanding of the oceanic world. One such event was the eruption of the Volcano off the coast of Iceland in 1963, which created a new island, providing scientists with a unique opportunity to study how life colonizes new land. Another significant discovery was the 1993 eruption of the Volcano, one of the most active underwater volcanoes in the Southwest Pacific. The Kavachi's eruptions have been a subject of study for understanding the dynamics of submarine volcanism and its impact on the ocean environment. Yet, the apocalyptic potential of these underwater behemoths cannot be understated. They hold within them the power to trigger massive tsunamis, potentially devastating coastal communities thousands of miles away. The eruption of the Krakatoa volcano in 1883, though primarily above water, demonstrated this destructive capability, with its resultant tsunamis killing tens of thousands of people. The possibility of a similar event, triggered by an underwater volcano, is a chilling prospect. This ominous threat casts a shadow over the future of volcanic research, a field that is becoming increasingly crucial as we grapple with the unpredictable nature of these geological titans. This ominous threat opens the gates to a realm where the future of volcanic research is not just a field of scientific inquiry, but a race against time. The field is rapidly evolving, integrating advanced technologies like artificial intelligence, satellite imagery, and deep-sea robotics to understand the enigmatic behavior of volcanoes. These tools are shedding light on volcanic activities in previously inaccessible regions, offering a glimpse into the hidden dynamics of Earth's interior. However, with each discovery, the unpredictability of volcanic eruptions becomes ever more apparent. The question that looms large is not just when the next eruption will occur, but how we can harness these technological advancements to predict the unpredictable. The endeavor to understand and forecast volcanic eruptions is not a solitary pursuit, but a collaborative international effort, where the global volcanic network emerges as humanity's watchtower. This network, a consortium of volcanic observatories and research institutions worldwide, functions as the eyes and ears of the planet's volcanic activity. Through this network, data from seismic sensors, GPS stations, and other monitoring tools are shared in real time, enabling a coordinated response to volcanic threats. This collaboration transcends borders, uniting the world in a common goal: to safeguard humanity from the wrath of these unpredictable giants. Yet amidst the ominous shadow cast by volcanoes, there lies a silver lining. From the catastrophic fury of eruptions, new lands rise, and fertile soils are born. The same fiery inferno that spells doom also breathes life, creating ecosystems where none existed. Volcanoes, in their paradoxical existence, are both destroyers and creators, painting a vivid picture of the circle of life on our dynamic planet. Islands have emerged from the ocean depths, forged by the fiery crucible of underwater eruptions. The soils enriched by volcanic materials are often incredibly fertile, supporting lush vegetation and diverse ecosystems. This paradoxical nature of volcanoes is a reminder of the delicate balance between destruction and creation that characterizes our planet. Furthermore, volcanoes are a source of geothermal energy and mineral resources. The heat generated by volcanic activity is harnessed to produce clean, sustainable energy, a resource that is becoming increasingly valuable in our energy-hungry world. And within the heart of these fiery mountains lie untold mineral riches, from rare metals to sparkling gemstones, a trove of treasures waiting to be discovered. As we continue to unlock the secrets of volcanoes, we tread a path fraught with danger and discovery, a journey that could define the future of humanity in the shadow of these sleeping giants. Thanks for watching this episode of Beyond Discovery. Don't miss the video you see on your screen. You won't believe it.